This is a video on the Wittig reaction, which is at a level which is appropriate for the carbonyl chemistry portion of the second year organic and biological chemistry module. So the Wittig reaction is a reaction between a carbonyl compound, typically an aldehyde or a ketone, with one of these quite strange looking species over here, which is an ylid. It can be spelt with or without the E, either is valid. But what an ylid effectively is a species with a formal negative and a positive charge on adjacent atoms. So there are lots of different types of ylids, but the most common ones and the ones that are used in the Wittig reaction are these phosphonium ylids, which are obviously based on phosphorus. So these two species react together to form either an E or a Z alkene, and we'll get on to stereochemistry later. But the thing to note for now is that the R group and the carbon, which were part of the ylid, end up at one end of the alkene, and the R group and the carbon, which were part of the carbonyl, end up at the other end of the alkene. So this is a very powerful way of making specific alkenes with specific functionalities on them. The other part of our starting materials, the oxygen from the carbonyl and the triphenyl phosphonium group, end up as our byproduct, which is triphenyl phosphine oxide. So how do we make these ylid species? Well, we typically start with an alkyl bromide. And if we take an alkyl bromide and treat it with triphenyl phosphine, the phosphorus has a lone pair on it, which can undergo an SN2 substitution on the alkyl bromide, and we end up with this salt species, which is called a Wittig salt. So you can see the phosphorus is now a hypervalent cation, and we have Br- because it's taken the electrons from the carbon-bromine bond. So a lot of these are commercial, you can buy most of them, or if you can't buy it, you can make it from the relevant alkyl bromide. So how do we get from here to the ylid? Well, we treat it with a strong base. And what this does is it takes the proton, which is adjacent to the phosphorus, and deprotonates it. So we're taking the proton off of here, and we're pushing the electrons from the CH bond back onto this carbon to give us a formal negative charge on carbon, and that is our ylid. Now, we can draw a resonance form of this ylid, where we push this negative charge off of carbon and onto the positively charged phosphorus, to give us a neutral species which has a carbon-phosphorus double bond. And this is the resonance form of the charged species. And both of these are valid, and both of these are perfectly good ways of drawing ylids. And I'm going to show you why I choose to draw ylids in this carbon-phosphorus double bonded form. So I've introduced it first as the charged form because the charged form explains the reactivity quite well. So if we take our ylid and we treat it with an electrophile, then this negative charge over here behaves as though it's a lone pair, which it effectively is, and it's nucleophilic, so it'll attack the electrophile like this, and we'll end up with our product where we've added our electrophile onto the carbon. Now, we can do similar things with this carbon-phosphorus double-bonded species if we treat that with an electrophile. Effectively, what we have here is a polarized pi bond, where the carbon is more electronegative than phosphorus, so when we push this bond onto the electrophile like this, the carbon takes the electrons and forms the new bond, and it takes the electrons away from phosphorus, so phosphorus is left positively charged. So we end up with the same product no matter which resonance form we use, we just have to draw them in slightly different ways. Now, the reason that I like drawing ylids in this fashion is because it's directly analogous to if we have a Grignard reagent, for example, where you're pushing a highly polarized carbon-metal bond onto an electrophile to form an alkylated species. You wouldn't tend to draw Grignards like this, where you have an isolated negative charge unless there was something there stabilizing it. And similarly with organolithiums, you tend to push the highly polarized sigma bond as well. So in order to keep everything consistent, I tend to draw my ylids like this, and as such you can think of them kind of as an extension of organometallic reagents like that. So in our mechanism as a whole, our ylid is going to come into contact with our carbonyl compound. It's going to attack it as a nucleophile, and that behaves in exactly the same way as you've seen with organolithiums and Grignards and things like that. So our nucleophilic portion attacks the carbon of the carbonyl, and we push the electrons up from the carbon-oxygen pi bond up onto oxygen to form a tetrahedral intermediates. Where the Wittig reaction kind of diverges a little bit is that your tetrahedral intermediate has this triphenyl phosphonium species hanging onto it, and that's going to react with our oxygen-centered anion. The first thing we need to do to make that happen is we need to rotate around this central carbon-carbon bond here to bring the oxygen and the phosphorus into close proximity, and the oxygen can then directly attack the phosphorus, like this, to form a four-membered ring, which is called an oxophosphate. Now, the following arrows look a bit strange, but what's effectively happening here is that your carbon-oxygen bond, your carbon-oxygen sigma bond is then breaking, and we're forming a phosphorus-oxygen pi bond, and your carbon-phosphorus sigma bond is breaking, and we're forming a carbon-carbon pi bond, and that's all happening in a concerted process all at the same time. So we're kicking out triphenylphosphine oxide as our byproduct, and we're making our alkene. Now I've drawn this as the cis alkene, but we can make both the cis and the trans alkenes from this reaction. It just depends on the structure of our substrates, so let's explore the stereochemistry in a little bit more detail. So the stereochemistry of the alkene that we get out of the Wittig reaction is determined by the relative stereochemistry of our oxophosphate intermediate. So whether or not we get the Z or cis alkene or the trans E alkene depends on whether or not we have the syn or the anti oxophosphate. So over here we've not drawn any stereochemistry in on this oxophosphate intermediate, so let's do that now. And our two options are we either have syn, relative stereochemistry, so our two R groups, the one that came from the carbonyl and the one that came from the ylide, are on the same face of the molecule, or they're on the opposite face of the molecule. I should point out at this stage that these are racemic, so we've got an equal amount of the hash isomer in this case, and the hash wedge enantiomer in this case as well. But I'm just going to stick with a single enantiomer just for clarity's sake. So if we draw this compound out as a sawhorse projection, we can see that just by tipping the ring up on its edge, both of our R groups now are on the same face of the ring, which is what we've represented here. And if we draw this one out as a sawhorse, we can see that our R groups are on opposite faces of the ring. So if we put in our arrows that we saw before, right, we're breaking this carbon-phosphorus bond and forming our carbon-carbon double bond, and we translate that onto our sawhorse projection, this step is concerted. Everything sort of leaves at the same time. All these bonds form and break at the same time. So wherever these two R groups are in this intermediate will be where they end up in the products. So you can see they're syn in this intermediate, and they end up cis in the alkene product here, which is exactly what we've got over here. And then if we then translate everything down here, the anti-oxophosphate, where the two R groups are on opposite faces of the four-membered ring, end up on opposite faces of the alkene afterwards. So our syn oxophosphate gives us our cis or Z alkene, and our anti-oxophosphate gives us our trans or E alkene. So we've determined that the syn gives us the cis and the anti gives us the trans, but what gives us the syn or the anti? Well, this is where things get a little bit complex, but I'll try and take you through it step by step. So the first thing that's going to happen is our attack of our ylide on our carbonyl compound can give us two possible stereoisomers. The first one is this anti-type stereoisomer, where our two R groups are on opposite faces of this molecule. And the other one is this syn-type isomer, where they're on the same face of the molecule. Now, I'm going to draw these as sawhorse projections, and we'll follow these through later. So this sawhorse projection here is this compound. And what you'll notice in both cases is that when the ylide attacks the carbonyl compound, the phosphonium group and the oxygen-centered anion end up antiperiplanar initially. Right? You can see they're antiperiplanar here. And if we draw this one over here, this one is also antiperiplanar. Now the difference is that our R groups in this case are on opposite faces of the molecule, and in this case our R groups are on the same face of the molecule. So these intermediates are stereochemically different, but they're both antiperiplanar with respect to the oxygen and the phosphorus. Now if we rotate around the central carbon-carbon bond, which is the next step in our reaction, we end up with these intermediates. Right? This is just from rotating this top portion of the molecule around, so the phenyl ring's gone around this way, and the oxygen's come around to the right-hand side. We've not flipped the stereocenter, that's just rotating around the central carbon-carbon bond. And we can see that this intermediate now is syn type, if you like. It's the same compound, it's just been rotated. And then this allows us to close onto the phosphorus and get to our syn oxophosphate. So our syn oxophosphate actually comes from an anti-type intermediate to start with. And if we do the same thing over here, our our syn intermediate, when we rotate it around, becomes an anti-type intermediate. And then when the oxygen closes onto the phosphorus, we end up with our anti-oxophosphate. So one thing to note now is that our initial intermediate over here, this syn-type intermediate, has a steric clash in it, which I've indicated with these red bands here. So the R group and the phenyl group are close to each other, they're sterically clashing with each other. So this is quite a high energy intermediate. And you'll notice in this intermediate over here, there is no such steric clash because the R groups are on opposite faces of the molecule. So one thing we can say is that the formation of this intermediate from the starting materials will be fast, or if you like it in sort of thermodynamic terms, it will be favoured. So I'm going to use kinetic and thermodynamic terms pretty much interchangeably, and you'll see why in a moment. So either this equilibrium is weighted in this direction, or it's a very fast kinetic reaction. Because this steric clash exists, it's not very favourable to form this intermediate, so as a result this reaction is slow, or if you like, it's not very favoured in terms of equilibria. Now, what happens when we then rotate around this carbon-carbon bond in this intermediate to get to this one? Well, if we watch what happens in the sawhorse, we introduce a steric clash. Let me just roll that back for you. So we start from an anti-periplanar intermediate. We're going to rotate this oxygen around to become syn-periplanar so it can react with the phosphorus. Watch what happens to this R group in proximity to this R group. It goes around and it introduces a steric clash. So this intermediate is now this one, or this conformer I should say. So in rotating around this central carbon-carbon bond, we introduce a steric clash, and that makes that process here relatively slow, or disfavoured if you like. So it's not very favourable to rotate around that carbon-carbon bond to get to this intermediate because you're introducing a steric clash. On the other hand, if we look at the sort of blue intermediate over here, when we rotate around the central carbon-carbon bond here, we alleviate that steric clash that was there initially. Let me just roll that back and show you again. So oxygen and phosphorus are anti-periplanar. Steric clash exists between these two R groups. As we rotate around to get the oxygen and the phosphorus syn-periplanar, the R groups are now on opposite faces of the molecule. So that steric clash is alleviated. As a result, this step over here is fast, or favoured, if you like. So what we need to do is just combine the oxygen and the phosphorus, and that will get us down to our syn-oxophosphatane in this case, or in the case on the right, it'll get us down to our anti-oxophosphatane. So we've studied the kinetics or the thermodynamics of each of these steps and each of these intermediates, and I'm now just going to abbreviate that in this form, and then we'll see what happens when we change the characteristics of the initial addition. Okay, so if our initial addition is reversible, so this reaction here between the ylide and the carbonyl, if this is reversible, that makes both of these reaction arrows over here equilibrium arrows, right? So we can move from starting material to this intermediate and back again, or to this intermediate and back again. Then what will happen is if we put our 10 representative molecules of starting material here into this reaction, we'll set up an equilibrium across these three species. So because this step over here is favoured, right, this is the intermediate which didn't have a steric clash in it, the equilibrium will be weighted in this direction. And because this intermediate over here is the one that had the steric clash in it, we can see that the arrows are moving back in this direction, so the equilibrium will be weighted over this way. However, the following step from both of these intermediates, this one over here is fast, this one over here is slow. So even though we've got a lot of molecules in this intermediate over here, the following step is very slow. That's the bond rotation to form this syn intermediate here. Whereas this one over here is very fast. So even though we've got fewer molecules on this side of the equilibrium, the following step becomes very fast. So these molecules that have made it over here to this intermediate will rotate very quickly. The oxygen and the phosphorus will combine to form the oxophosphatane, and you'll end up with transalkene. Now, what we've done is displaced the equilibrium here. We've removed product from one of the sides of the equilibrium. So by Le Chatelier's principle, the equilibrium will now work to resist the change that we've made. and we'll re-equilibrate the system via the starting materials back to something similar to what it had before. So let me just show you that happening again. So we're taking intermediate over here, moving it back through the starting materials and back over this side. And we can do that because this initial step is reversible. Again, because this is very fast, we'll then have molecules zipping through this side of the reaction. Now, occasionally, one of these molecules over here, one of these intermediates, will go and undergo this slow bond rotation to form this intermediate. The oxygen will close onto the phosphorus and we'll end up with cis-alkene. But by and large, the majority of it will be zipping through very quickly onto this side, re-equilibrating, and eventually we'll end up with a majority of trans or E-alkene. So if your initial step is reversible, so you've got an equilibrium across these three species, then because this step here is very fast, you'll drag all of your starting material through this manifold on the right, and the majority of your alkene will be trans. If, on the other hand, your initial addition is irreversible, so the addition of the ylide into the carbonyl is irreversible, there's no going back once you've added into this carbonyl and formed this tetrahedral intermediate. Both of these reaction arrows here become irreversible reaction arrows, there's no equilibrium set up. Then if we feed in our same 10 molecules of starting material, then this reaction over here is kinetically faster than this one, again for the same reasons, because this one doesn't have a steric clash in it and this one does. So what will happen is all of our molecules will make a choice, and generally the majority of molecules will go for the faster route over here. So we'll end up with a large concentration of molecules in this intermediate and a small concentration in this intermediate, the same as we had before. So this following step is still very fast, and we'll continue to drag molecules through it onto the E-alkene. However, there's now no longer an equilibrium between these three species. So even though we've removed these molecules from this intermediate, Le Chatelier's principle now no longer applies. We can't drag material back through this way to re-equilibrate the system because this step is irreversible. So all of these molecules over here, which have taken the fast initial addition step, are now stuck here, waiting for this very slow drip feed of bond rotation, closure, and then forming the cis-alkene. So all of these intermediates have no choice but to sit here and wait until eventually they become cis or Z-alkene. So if your initial addition is irreversible, you end up with a majority of the cis or the Z-alkene. So what determines whether our initial addition is reversible or irreversible? Well, it's to do with the nature of the ylide. So again, I've drawn it out as both double bonded and charged resonance forms. And it's easier to see with the charged resonance form because it's to do with this negative charge here. So this negative charge is the nucleophilic portion of the molecule. It's what's doing the attacking on the carbonyl. And we're forming this intermediate here. So if this step is reversible, the arrows for the reverse of this reaction are these ones. We're pushing the electrons back down from oxygen to reform the carbonyl. We're breaking the carbon-carbon bond and we're pushing the electrons back onto carbon. So this reaction here, these arrows, are forming this negative charge. So the more stable this negative charge is, the more likely this process here is to occur. So you can think of it in terms of if this negative charge is more nucleophilic, i.e. less stable, your reaction will be less reversible. If this negative charge is less nucleophilic, i.e. it's more stable, then this process here will be more favourable and your reaction will be more reversible. So we can categorize ylides as stabilized, non-stabilized, or what are called semi-stabilized. So by stabilized ylides, we essentially mean something which has an anion stabilizing group directly attached. So if we have our negative charge on our ylide here, you're going to be able to draw a resonance form where it resonates with phosphorus in any case. But now we're looking at what's on the other side. So this is adjacent to a carbonyl. We know that carbonyls are excellent anion stabilizing groups because this is effectively an enolate. So if we draw this resonance form here, you have a nice oxygen-centered anion in your enolate resonance form. So this is a highly stabilizing effect. It's making this negative charge more stable, less nucleophilic, which is giving you a reversible addition. And we know that reversible initial additions give you the trans product. So if your ylide is stabilized, it has a strongly anion stabilizing group, like an ester, any kind of carbonyl group really, nitro groups, nitriles, that sort of thing. Resonance stabilizing groups will tend to give you the trans product as a major product. If your ylid is non-stabilized, so there's nothing next door which can stabilize this negative charge, this is just an alkyl group, the only resonance form you can draw is with the phosphorus. This will give you an irreversible initial addition, which, as we know, gives you the cis or Z as a major product. Then come the problematic ones, things like benzylic ylids. So in this case, yes, you can draw resonance forms, but they're all carbon-centered. This is not as stabilizing as having a carbonyl or a really strongly anion stabilizing group. So what tends to happen in this case is you have a mixture of the reaction pathways, a partially reversible addition, and this gives you a mixture of isomers, which unfortunately you're going to have to separate. So the take-home message is the stabilization of your ylid will determine what your stereochemistry of your alkene is. So stabilized ylids give you a reversible addition, trans alkenes, non-stabilized give you irreversible addition and cis alkenes. Anything else in between, you tend to get a mixture of isomers.